Welcome to the Macho Black channel. This is the first chapter of subject A213 or subject CM1, the South African version. This is just a summary of my notes. Go through the summary and try and explain it, and hopefully do some questions, which should show, or hopefully show that the summary is on point, right? So the life insurance contract is what the policyholder buys from the life insurance company. Second point that's important there is that the benefit is linked to the premium. So for you to get a benefit, you need to pay a premium as the policyholder. So the benefit is an income to the life insurance company. Well, the premium is an income. Sorry, and premium is an income, and the benefit is an outgo, goes to the policyholder. So both of these could be single, or they can have multiple frequency, or either or vice versa, in any order, no specific order. So next point is the benefits are conditional to some kind of event that needs to happen, and the premium has to be paid in advance. So the present value of the outgo, so this is from the perspective of the life insurance company. So the present value of whatever goes out needs to be equal to the present value of the income. And then further down, attaching probabilities to that is that the present value of the outgo, or the expected present value of the outgo, needs to be equal to the expected present value of the income. So whenever we are calculating premiums, we will see that if we're calculating recurring premiums, they would be in the form of an annuity due, but we'll get to that later on. The interest needs to be known at inception. Yes, the interest needs to be known at inception. So we're going to introduce the first probability, which is the probability of, okay, let's first define, before we introduce the probability, let's first define the force of mortality, right? We're going to define it and not explain it yet, right? But the force of mortality is a rate of transfer from one stage to the next. In this case, the rate of transfer from alive to dead, right? Because we are dealing with the life table and life contingencies. So, I mean, if you're familiar with other statistical courses, you would have gone through this in a deeper form. But for now, the force mortality is a rate of transfer from alive to dead. And the first probability we're introducing is TPX, which is the probability that a life aged X will be alive after T years. So that is just equal to the exponent of the negative integral of the force of mortality from time 0 to T, which basically represents the T on the side. We should do an example later on that will kind of explain this, but I mean, this is the formula that, you need to know the definition of. Moving on this force of mortality, we then add a DS factor, or we just multiply the DS factor or that integration factor, right? So we're going to say UX multiplied by DX. Then we get the probability that a life aged X plus X dies between age X plus S and X plus X plus D. So you're just adding the next instant of time, basically. And then if you multiply this factor by a by the probability of life function, we then get that this is a life aged X living for S years, denoted by this, and then dying in the next instant of time. So that DS is just putting an end to the life. The next important probability is just the opposite of TPX, which is TQX, right? So that would be the probability while I mean TPX is the probability that the life will be alive after T years. TQX is a probability that the life dies at any point between now and T years, right? So the formal definition would be the probability that X dies at any moment over the next T years. So, I mean, it's really advisable that you familiarize doing this in Word. Hence, I've not written it on the paper. I've sort of typed it down. So if you do need a tutorial on how to sort of write these functions on Word, just shout. And we can do that as well. So this is then an obvious function that says TPX plus TQX is equal to 1. So this is just the probability that you may be alive and then and die at some point, or if you're not alive, then you're dead. If you're not dead, then you're alive, and that is equal to 1. Okay, cool. Moving on. We then have that for this particular course that we're doing, the mortality is dependent on age or age plus durations in some event like underwriting, but currently it's dependent on age. The next important formula is something called the principle of consistency, which basically states that if I'm alive now, okay, so it just says TPX it just says the probability of a person age X, and if that person needs to live T plus X years, then you can split that probability into two probabilities, where the person aged X first lives for T years, and then there'd obviously be X plus T years when that prevails, and then leaving an additional S years. Or you could inverse that or swap the T and the S where the person lives for S years. And then there'd obviously be H X plus S living for T years. So that is the principle of consistency, and um, we'll see how it's going to be used further on in the uniform debts distribution of debts that we'll be doing. Um, Moving on, we then move on to something called the life table. The importance of this life table is that it starts at a high value and then decreases, like a group of people, group of 10-year-olds. You study them for the next, I don't know, 30 years. So some will drop, some will die, and then after 30 years, you'll be left with X number of students. Like this was measuring a degree at some institution, number of students in the program, or number of students that either fail or pass, basically. So the pass sort of decreases over time. So that is the life table. The first value, which is L0, is called a radix. Um, so that's basically what we need to understand about the life table. And there's 4 formulas that we need to understand about the life table. So the probability of the next life, right, is equal to this life multiplied by the probability of survival to the next age. So which means the number of lives alive at age X plus 1 is equal to the number of lives alive at X multiplied by the probability that they make it through X. TPX, which is the probability that life age X is alive after T years. So that is equal to the probability is equal to the number of lives alive at age X plus T divided by the number of lives alive at age X. So obviously, if no one dies, these will be equal, and the answer is going to be 1. The next formula, which is dx, which is the number of lives that die at age X. So that is equal to the number of lives that are alive at age X minus the number of lives alive at age X plus 1. So the difference is the number of deaths. So, I mean, if the force of mortality or the force of removal, whatever is 0, then we will have dx as 0. So the force of mortality is equal to, there is a proof that's in the notes or whatever, and it's important, I think, to sort of know it. It's just that it's the derivative of ln x. So if you're given a function, say of x, and they say calculate the force of mortality at 8x, you just find the derivative and then substitute whatever values are there. Okay, so we then move on to the lifetime random variables. So the lifetime random variables, the first important element there is Tx. So Tx is something called a complete lifetime random variable. So it's just a complete lifetime random variable, or basically how long a person is meant to live, or it's the exact length of the remaining lifetime of life. So that is Tx. So this Tx obviously has a PDF, which is a graph that, it behaves by, and that PDF is given by SPX multiplied by the force of mortality. That is then, we then have a CDF. So PDF is a probability density function, and CDF is the graph that we use to calculate the actual probability. So the CDF of your life would basically end when you die. So it should be a function of your death, which is TQX, the integral of the PDF, SPXUX plus XDS, and that is equal to the probability that Tx is less than some finite t. Okay. I'll do a video of how we can apply these formulas. I'll probably do 5 examples, and then leave the remainder of the examples for the revision. And most of our examples will come from the past exam papers. So the CDF, which is a function, we can have the expectation of Tx, or the expected Tx, which is just that CDF multiplied by T. And then we have an integral over it. So it's the standard statistical formula for the mean, or it's a standard formula for the mean or the expected value of life, right? But the important part is that the ETX simplifies to the integral from 0 to infinity of TPX dt, and that is equal to another function, which is an E and a 0 at the top and an X at the bottom. And that function is called the complete expected future lifetime, or the complete expectation of life. The keyword is complete and expectation. But the important part is that when using a continuous function, we just have that E with the 0 at the top. And another function, which is kx. So we had tx, we have kx, which is just the integer function, or the discrete value of tx. So it's just the integer part, or the integer value of tx. Okay, so how we calculate this, we'd obviously need to calculate some PDF of kx, and then get to a CDF, and then eventually get to an expectation of value. But before we can do that, we then have to introduce a new function, which is a QX that has a different version, or it has bells and whistles, right? So we have QX, and then there's an M on the side, which represents the normal TQX. But then this bar and the n before it says that the life first has to survive the n years and then die within the m years. So is that a life aged X will die, or a life aged X will live for the next n years and die for m years after that, or a life aged X will die between ages X plus n and X plus n plus m. So that is the definition of that QX. And then, I mean, sort of understood it with the PX because the life aged X needs to live for X for n years, and then they will be X plus n years at the time, and then die at age um, X plus m or the next m years. And then this is just the L, writing it in LX format, in life tables format. Both functions are important because depending on how they ask the question or what information you have on the question. Right, back to our our KX. So KX is the probability that KX is equal to K, then becomes equal to this n bar MQX function, right? But the m is a 1. So there's a, whenever it's QX, just know that the 1 is invisible. So the life needs to live or die within um, the next year. So in this case, it's a life dying within the next year. So the life lives for k years and then dies in the next year. If it's a PX, then the life will be alive after 1 year. Okay, so that's the PDF of K, which is a discrete function, and then KQX, the expected value or expectation of KX is just equal to the sum, where we're doing the integral of the PDF here. We are doing the sum here of the PDF, which you can write in those functions. And then simplifying that, you get the sum, where k starts at 1 to infinity at kpx, right? Similar to that tpx. And then you just get an e with the x subscript without the 0. And that is just equal to the continuous version of it minus half, which makes sense because, I mean, a continuous version would be complete. A discrete version, you'd have some rooms for error or would be less. So that is then defined as the catate future lifetime of X, catate future lifetime of X. Moving on to the second last part of this life table is we then have two approximation methods, right? The one method is constant force of mortality, and the other is a uniform distribution of deaths. So when you assume a constant force of mortality, your TPX is, so your T here is going to be less than 1, right? And then you're just going to have your PX, which is just the age rounded down. We round the age down, not up. So it's just the age rounded down to the nearest integer, or the integer part, I guess, not rounded down. So the x is the integer part to the power t. So it's px. Remember, there's a 1 here, right? So it's just px to the power t. And this very same px is that tpx, but now you have um, S, you have a condition where T and X is less than 1, right? So that would be if you have 0.25 and 0.75 or whatever, but S plus T normally equals 1. But we'll have an example of that um, as well, where we'll discuss it. But this is just a formula to know as well, right? That you need to know. And then we have um, the uniform distribution of death. So I guess constant force of mortality means from age, I don't know, 20 to age 80, the mortality is the same, right? And then uniform is constant. Yeah, mortality is constant. Then uniform distribution of death means the mortality is equal at each age interval. So for uniform distribution of death, the important formulas are that if you have S alone, right? Like you have half, right? If S is greater than 0, less than 1, then SQX um, is equal to the integral of QX dt, which is just S multiplied by QX, right? If you have two two values on this side, which we'll also explain as well on the example, that then you would be using this formula here, which is T minus X QX plus S, same QX formula, but there's a T minus QX, 1 minus SQX. The important thing is that whenever you're dealing with with UDD or uniform distribution of death, using QXs, right? And the X is an integer function. And then when using constant force of mortality using PXs, which is the life functions, and you just have to play around with that, with those formulas. Okay. Feel free to ask questions. Happy to explain. And then going on to, but you just need to understand first principles. You need to understand integration. You need to understand summing. You need to understand, I don't know, first year math. And then you have something called select mortality. So for select mortality, your age X has a bracket. Let's say you're 20 and you buy life insurance and then you do some underwriting. And then at age 25, instead of it being LX, it will be L20 plus 5 because you've been 5 years since you did your underwriting, right? So, I mean, um, the so it's denoted as, I don't know, X in brackets, square brackets plus R. So the brackets replace the X, and then the R is the duration that has passed since mortality. And then you have, so you have, duration 0, duration 1. Most tables go up to duration 5, right? So at duration 5, then, I mean, if it's duration 0, like a 35-year-old enters a policy now, then it will be X in brackets. If they entered last year, it would be an X in 34 plus 1, right? Which is still a 35-year-old, but with 1 year uh, underwriting. Duration 2 to 4 is tricky. It's not necessarily equal depending on the forces, um, whatever, but you're still representing the same ages, the same age, but at different points of mortality, right? And then normally at duration 5, let's say uh, this guy, I don't know, at age 40, they'll be using the normal life tables, right? Because after 5 years, I think any form of underwriting sort of goes away. So the last part here that is important is you have a recurring formula. So this formula is to calculate your own life table. So this helps you calculate your own life table or any values of the life table. So the first part would be this part, this fourth part. So this just says Lx plus 1 is equal to Lx multiplied by the probability that you're alive. So 1 minus the probability that you're dead is the same as the probability that you're alive, right? And then the second part is that Lx plus t is equal to Lx plus t plus 1 over, again, this is, the probability that you're alive, 1 minus Qx plus t. So, I mean, this formula just needs one to remember because you'd probably be given a life table that's incomplete, and then you probably have to fill in some values in the life table that is select, and then this formula will come in handy. M92 is a very popular table that you're normally asked. So it's important that, you know that after 2 years, then Lx plus T, you know, there's no selection. So Lx plus T is the same as Lx plus K, right? Um, yeah, I guess this needed to be a T. Oh, T. Okay, so after 2 years, there's no mortality. And yeah, that is the gist of it. Um, young 2 pages or 3 pages. I think there's like 7 key formulas that we need to remember. Um, and then once we remember these formulas, these are the formulas that will actually help us do the examples on the next page or the next video. But yeah, the next video will just continue. So the important things to remember here is that, I mean, we're not cramming these formulas. We want to sort of make these teachings stick. So, I mean, you need to be able to retrieve this information without cramming it per se. So we need to work on our retrieval or our memory strengths. We also need to leave space before we learn another concept. So we're gonna do examples. You obviously need, after the examples, you need to go back. There's also some more examples. You can contact me and then I can send you the examples. You can go through the past papers. And that will also just space out your learning over new concepts. Let this one marinate. And then practice, you know. Um, we'll just go through exam technique. That's why we're just using examination examples. So that just helps us when we're reading questions, what should go into our minds. I don't know. Learning styles, I don't even want to comment on that. Um, and then, yeah, it's just easy to make mistakes along the way. If you don't make mistakes when you practice, then, you'll fail the paper. So it's easier to make these mistakes uh, during practice, and then you'll fail the paper. So yeah, hope this was good. See you on the next one. Cheers.